pleased to announce Rick Miller will be starting off the show today. Rick is a professor emeritus from Oregon State University. Rick has worked in the plant and fire ecology of sagebrush and juniper woodland ecosystems in the Intermountain region for nearly 4 decades, primarily out of the Northeast Oregon Great Basin Experimental Range Station. If you'd please welcome Rick Miller.
Okay, thank you. Well, it's definitely an honor to be the first speaker up, and it's always nice to be the first one up because then I can relax for enjoy the rest of the symposia. What I'm going to be spending a little bit of time on this morning is covering the Pinyon-juniper woodland component, and mainly kind of hitting briefly, because I don't have the time on these topics, in terms of describing the woodland component and looking at that interaction with sagebrush communities. We'll look at restoration and dynamics. I feel like we really need to understand the dynamics of these systems when we think about restoration, because oftentimes we're shooting at moving targets that are changing all the time. And then talk a little bit about concepts of resilience and resistance, and really think about what really is it that we're restoring, and are these concepts useful? Well, you can get in the literature and you can't even get agreement when it comes down to just how much pinyon-juniper woodlands do we have, anywhere from 42 million to 80 million. The 42 million is probably a conservative estimate just for primarily Great Basin woodlands of Osteosperma, Utah, western juniper, and probably mostly Monophylla. And we push up into the 80 million, we're getting over into Monosperma, we're picking up Depiana, and so that's kind of the range. And so it is a moving target depending on what is being defined as a woodland and what is not a woodland. These woodlands occur across a lot of different types of geological and landforms, which makes them very heterogeneous when we think about how resilient, resistant these systems are. The answer always gets down, well, it depends. They occur on volcanics, limestone, all kinds of sedimentary, broad range of soils from sands to clays, to clay loams, sand loams, silt loams. They seem to have a little bit of an inversion of not liking the heavy silt soils. Leonard did a lot of mapping of soils back in the 80s and pulled a lot of information together and mentioned that with its broad adaptability to a wide range of soils, that in the absence of disturbance, these woodlands would occupy a much broader range than they do today. The other component that's important to consider, and then elevation-wise, they broad range. When we're up in the Great Basin Colorado Plateau, the bulk of them occur between 4,500 and 7,500 feet. Of course, as you move north, the elevation drops to where you'll see most of the woodlands, but there's always the extremes. And for example, the White Mountains, you have these woodlands bumping right up into the very high elevations, right up into the limber whitebark pines and bristlecone pines. Oh, okay, good. A pointer. This will probably really mix me up here. See if I can. So as I mentioned, they do occur across a broad range of soils and landforms, from ridge tops to terraces, tablelands, valley floors. And they occur across a wide range of soils. And one thing that's important that I'm going to hit on kind of in and out of this talk, but particularly at the end, of the soil moisture temperature regimes that they occur on. The mesic and frigid, which is kind of a combination of what kind of moisture is available and at what time of the year, and the temperatures that it's interacting with. The majority of them are what we would call mesic and frigid, which are soil terms. Mesic is a very confusing term for ecologists because it means adequate moisture for growth, but if you're talking to a soils person, he says, no, that means these are warm soils. It has to do with the warmer temperatures. Frigid or cool, and you can think of cryic as cold, the higher elevation soils. We have the aeritic regimes, which are usually less than 12 inches, xeric more than 12 inch, and oostic, which means we've got a summer monsoon regime. And these are important because if you look at a soil name, you're going to see, it'll tell you right off the bat whether you're on a warm site, a cool site, or a cold site, and whether you're less than 12 or more than 12. So if you've never even been on a site and you look at that soil name, right away you're going to have some information in terms of what the ecology of that site might be. The key component, too, is on soils, which gets a little tricky. There's a lot of debate on what are woodlands and what are woodlands reestablishing into shrub steppe that weren't shrub steppe or shrub steppe that are being encroached. And Blackburn Fisher group, NRCS people in Nevada are working on having another tool to help separate these. And of course, when we think of the mollisols, because these woodlands occur on mollisols, iridosols, and entosols, but at least on the mollic horizons, which are more productive sagebrush communities, that forest soils typically have no or a very thin mollic horizon. And I think it's a work in progress, but about 7 inches or less. You probably have a soil that wasn't a productive sage steppe, but if you have it where it's thicker than that, this is likely, for example, on this site, if it had a thicker, which it does have a good mollic horizon, this site here for a long time has been a mountain big sagebrush grassland site and not a woodland. So that's a tool along with looking at age structure and looking for old wood around on the site. The only problem is if you're on a iridosol, of course iridosols don't have mollic horizons, and this would be the lower belt of the juniper component moving into some of the drier sites. It gets a little trickier, moisture is going to be the limiting factor. And here in this this is an old woodland that's been there a long time, but it's always been a very open woodland, which a lot of the paleobotany information seems to indicate a lot of these woodlands in the past tended to be more open than they are today. But it does have a mollic horizon, but it's a very rocky skeletal site, which is typical for a lot of more persistent juniper woodlands tend to be skeletal, or here in the Colorado Plateau or Great Basin, they tend to be very cobbly to rocky soil surfaces. A broad range of precipitation, but again, the majority are probably found within 10 to 16 inches, but again, you can get out into a wider range. But one big component, again, it kind of gives you, when you think of the broad geology, broad soils, and then the precip patterns here of the kind of heterogeneity that we're looking at when we talk about pinyon-juniper woodlands. And here where we go from, this is a monsoonal gradient down as we move from the northwest to the southeast. You can see how the monsoonal effect really changes. And we have, of course, the Great Basin, which would be right here where we have the Uinta Mountain Range where the break is. We're pretty much off in this direction. We're looking at 25% or less of the total. And then you can see the increase of around 30-35% till we get into down in this zone where we're talking, more than half of the precipitation comes this summer. So there is quite a gradient where we have western juniper here occurring mostly where it's 15% or less. This looks like western, but this is actually used to be Occidentalis australis, the Sierra juniper, which is now Juniperus grandis. They're continually changing names, which I keep thinking one of these days I need to retire because I can't keep up with the name changes. We can see that Utah juniper really has quite a range where it bulkily comes up into this northwest kind of part of the Great Basin region, and it does actually go off on this over into this part of Utah and even down into Arizona, and to where you're pushing maybe almost a third of the summer precip is monsoonal, summer precip, and then once you kick into greater than 35%, you start picking into monosperma, and Depiana is also strongly tied to a strong monsoonal influence. The juniper, the pinyons are a little more well-behaved in terms of it's kind of nice with Great Basin or single needle pinyon pine kind of butts right up against the Uinta mountain range here, 25% or less precip, and then we pick up the edulis, which occurs off in this direction here. We do have a mix down here with edulis occurring, which is a variety phalanx, which probably is possibly influenced by this Baja, more of a Baja monsoonal influence than it is from the Gulf. And then you have Rocky Mountain juniper. I'm not going to really address that today other than saying that it does break out from the other junipers. If you look at temperature maps, it definitely occurs on the cooler sites. This, as we know, that the juniper pinyon component is closely tied with sagebrush. It has been for a long, long time period. Typically, where we have shrub steppe communities at the low elevation belt, where it could be shrub steppe or it could be desert, more of a sage shrub. We get our more mountain shrub or mountain big sagebrush communities up above the belt, as we can with more different types of conifers. And then in many areas, it also intermix, and it can be a real mosaic, where it's kind of been a back and forth thing with either Wyoming big sage or mountain big sage or black sage, low sage. There's a number, those are probably the majority, make up the biggest component. And as I mentioned, they can butt up against mixed conifer, particularly as you move, not as much as you're up in more the northwestern part of the Great Basin, but as you move to the southwest, you start picking up more of the mixed conifer. And even if you're in the White Mountains, the mixed conifer, you go from really pinyon-juniper right up into limber pine and bristlecone pine. So again, it depends on where you're located. So how about, let's take a look at the past, because really it kind of helps us know what these woodlands been doing and sagebrush have been doing over the past, and how have we kind of come to the time of what we think of pre-settlement, and then we move into where we are today, because they've had a very dynamic past. Well, if we go back, we know that the Wisconsin, the last glacial advance, it started around 120,000, 130,000 years ago. But it makes it kind of convenient to start here right at 18,000 years, right at the beginning of the graph, right in here, because that was the coldest period during the last ice age. So it actually was warmer prior to that, and then glacial max was around 18 to 22,000 years ago. And it stayed really very cold. It's when we had our high lake levels. We see a warming period, and then this is what they call the younger Dryas cold snap right before the break of the Holocene. Then we get into the Holocene, the last 10,000 years. We had a relatively, depends on where you were. If you were in the northwest part of the Great Basin, the first part of the Holocene was a bit dry, but not as dry as it is today. Lake levels were considerably higher. And then it went into this cool period. But if you move into down more in this neck of the woods down here, the early Holocene was fairly moist and cool. The Native American populations were actually at their high point during this time period because resources were good. Then we move up into this, what they call the mid-Holocene, considerably drier than what we have today. And then we get into the late Holocene period here, where we went into this neoglacial max, very cold. We went into the medieval warm period, and then little ice age, and then here we come in. We're going to take a closer look at this here in just a few minutes. Well, what's interesting is you can go back and look at the pollen records, macrofossil records, but particularly pollen records that go considerably farther back. And much of the Great Basin vegetation was present back a million years ago, 30,000 years. It was here during glacial max. And what made the Great Basin and parts of the Colorado Plateau so resilient is that the vegetation could quickly move and adjust to colder temperatures, warmer temperatures, wet conditions, dry conditions, by simply either moving up and down in elevation or moving from a south slope to a north or a north to a south. So this enabled the vegetation to move around relatively short distances. But also, so elevation aspect were a key component. But there were also a number of species that did migrate. And if we take a look at a couple of species we're interested in today, where we have the Edulis shown there on the map. We have Monophila, and then the subspecies I mentioned, which is a subspecies of Edulis that might be in there. Speculation of possibly a Baja influence of getting a little more summer precip. But you can see that Monophila, its farthest northern extent, which is right at that point there is the Owens Valley. And it did not occur in the Great Basin, nor did we have any pinyon in Utah or Wyoming at that time period. So right there with the bulk in Nevada, that's right around the Las Vegas area. Mountains now today that have no trees growing on them because it's far too dry. And this is what it looks like today. The earliest evidence of movement was right up, we have this is the White Mountains right in here, and that Right there was the earliest, first probably evidence of Monophila moving into the Great Basin, right at the very end of the outside of the Owens Valley on the north end of the Whites. But actually, the most rapid movement of Monophila was up along the Nevada-Utah border, and then you can see how much Edulis has expanded. So there's been a big change in movement, and Monophila is considered to have been here not near as long up in our part of the area as our junipers. In fact, the White Mountains, even where there was evidence of early pinyon in the Whites in the Owens Valley, Osteosperma was the dominant tree, where the Monophila was not, where today most of those woodlands are dominated by Monophila. Well, what were the juniper doing at this time? Well, they have a little more complicated story where you have western up here. Western didn't occur up in that neck of the woods or that area back during full glaciation. In fact, the only evidence of juniperus up in that area were common juniper and horizontal juniper. And these are very low growing that typically we find more in forest, colder, more mesic sites. The earliest evidence of western juniper we have would have been right up here in the Lake Winnemucca area about 12,000 years ago. But before that, we don't know where it was, and it didn't start moving up in here till about 6,000 years ago during the Holocene. I've talked to Peter Wigan quite a bit on this, and our only guess is we think that western at that time during full glaciation was up here in Northern California somewhere, maybe in the northern part of the Sacramento Valley. How about Utah juniper? Well, there's evidence, good evidence, that Utah juniper in this region right here was there 30,000 years ago, pre-full glaciation. It was there during glaciation, and it's been there since. If we get into this border here between Utah and Nevada, it was there 30,000 years ago. It disappeared during full glaciation, and then it reappears again during the Holocene, possibly with its northern extent being somewhere in Utah about where the Green River flows into the Colorado River. And my guess is what was going on is we have considerably lower elevation basins here. The valley floors here are pretty darn high. And most of where we think of PJ today is where we had bristlecone and limber pine growing back 18,000 years ago. So when we came, or just prior to Eurasian settlement, what did these woodlands look like across the landscape? And we've got to remember these are kind of snapshots in time. If you've read any of John Muir's writings, he talks about going across Utah and Nevada back in the 1870s, and basically writing this statement here that he saw this distinction of sagebrush basins and then forested areas. That seems pretty straightforward and simple, but then we take a look at, to me, one of the classic papers, Cottam and Stewart. This was work they did back in the 1930s. It was published in the Journal of Ecology in 1940, where they actually had good information on vegetation because there was an old massacre site, there was a fort there that they moved in later, and there was good information on vegetation, and they noted a 500% increase in the woodland component from the 1860s to the 1930s. And another interesting statement in the journals, the statement here is we headed up the Crooked River, which is in Oregon. We saw the occasional cedar tree up on the rimrock. And that was Peter Skane Ogden back in 1825. But to kind of cloud this issue, we also know that a lot of this landscape had been impacted by the Comstock period. Young and Booty estimate 600,000 acres of pinyon that was harvested to go in to make charcoal for mining, extracting the minerals, and I think Ron Lanner estimates about 750,000. If we look at Tueler's estimates of PJ in that mining region, this would be somewhere between 6 and 8% of the total PJ that would have been impacted. And then the question is, well, what's the difference? Do we have encroachment or do we have reestablishment going on these sites? Well, one thing that we have really strong evidence for much of these pinyon woodlands is there has been definitely a change in the age structure since 1850. that there's been considerable infill. So areas that we're pretty sure were woodlands in the past, based on soils, based on the presence of old trees and old wood, there's been considerable increase in density since 1850. Prior to 1850, these woodlands were probably more open, and much of the paleobotany data that goes back, say, the last 18,000 years, when they talk about these woodlands, they say there's evidence based on pollen records, macrofossil, that they tended to be more open, and I'm sure there was a considerable amount of variation. This is an interesting site on Pumice, where they went in and they harvested 95%, or they cut down 95% of all the young trees and left the old trees. And so this kind of gives you an idea of what this site would have looked like, probably with a lot more perennial grass. Now there's cheatgrass in the interspace. That kind of the structure of the woodland would have looked like around 1850. So what was going on to where we say, we see this increase in density throughout the Great Basin? And that's from Mesa Verde to Barger's work down south, up all the way up through Nevada and up into Idaho and Oregon. Well, we look at the last 7,000 or 1,000 years, we've got the medieval warm period, which was warmer than it is today. We go into the Little Ice Age, and then we can see this change here just around 1850. That during that Little Ice Age, there's evidence that there was a slow increase that typically, let me step back here a second, that woodlands would tend to increase during conditions that would become a little more mild and more wet, and then they would decline during periods that would be very dry. And so there is considerable evidence during this period here of moving into the medieval warm period that woodlands retracted. There were large fires with large charcoal. You had not a lot of fires during this period because there was little surface fuel, and then you start changing. You'll see a change here in the fire regime, but we get into this cooler period where it shows there was a slow increase in the woodland component. What's interesting here is that during this time period, right at the time we're settling, livestock are going on the landscape, we're seeing changes in fire regimes, we have a change in climate, that there's suddenly a very rapid increase during the late 1800s, late 1900s of the woodland component. And one thing is, during this late 1800s, there were some dry periods, but this generally was a relatively moist period. But then since really 1850, we've been going warmer or drier, so that's had some influence. And the mixed bag here is that these are great conditions for cone production, seedling establishment of woodland, but also you have mild moist conditions, which also would mean increased fine fuel loads, potential increase in fire, but then we just do see this change in livestock grazing, which remove fine fuels. And something that I just wanted to throw in here, I think a point you need to file away is that when we talk about potential natural vegetation, you're thinking time of settlement, just consider the kind of climate conditions where that potential natural vegetation was at compared to where we're going here, say 150, 160 years later. Well, one thing that was quite interesting is I mentioned the moist period, but Woodhouse looked at weather stations from Montana, Idaho, Washington, down through Oregon, Utah, Nevada, Arizona, all through the Intermountain West. And the one thing he said was kind of unique was this period between 1905 and 1917 where it was extremely wet conditions from southern Arizona all the way up into Montana and Idaho, which usually doesn't occur. A lot of times once something's happening down south, we're seeing some different things happen up north. So this was a real wet period during this time. And if we look at just a couple of chronologies, this is Barger's work down in the Escalante area. You can see they didn't finish off their dendrochronology here past the 1940, but you can see this peak that occurs right around 1900, 1920. And kind of this gradual increase and then a very sharp increase during that wet period. This is pretty common. This is some of our work up at the north end where you can see in Idaho and Oregon, we're seeing this similar peak in establishment right around this very tail end of the 1800s and early 1900s. So this wet period definitely had an impact on what was going on with establishment. And again, Grazing in some areas was having a significant impact in fire regimes, in other areas it was not, depending on where you're located. Expansion also, if you looked at areas that you feel these were sagebrush steppe woodlands, or sagebrush steppe communities, and you age the oldest trees to find out when did sagebrush or juniper start moving into these shrub steppe communities, the peak would be similar to what you just saw. The most rapid expansion into the sagebrush, it's still going on, we're seeing some of that today, but was during this 1800 to about 1920 period. So the question is, well, we mentioned climate was a factor, but rarely is one thing a component. How about fire, grazing, CO2, or how much of this is reestablishment? Knapp and Sol have done a lot of CO2 work, and they feel that there's a biological inertia going on with increased CO2 where we're still seeing expansion and recruitment of these trees in drier times. But how about fire grazing has been somewhat debated, so let's take a look at that. In terms of the effect of livestock on fire regimes. Well, some work, particularly up north, this is some of ours, where we looked at these little isolated pockets of ponderosa pine that were surrounded by sagebrush steppe communities, where this is work did with Emily Hardall, that basically these were areas that were very productive ponderosa pine fescue sites where we had a rich history of fire scars. We had a 8 to 12 year fire return interval on these sites. And then the date there shows you the last fire that occurred, and there hasn't been a fire on those sites since, and the bars show juniper, western juniper establishment of what's occurred on this time. And of course this area, 1870s when the livestock started moving in on this area. So besides climate, definitely livestock had an impact. And the other thing that we need to be careful of when we're talking about fire regimes is that we need to know, are we talking about what would have been persistent old growth juniper woodlands, or are we talking sagebrush steppe, because the fuels are going to be very different in terms of not just the abundance of fuels, but particularly the abundance and continuity of surface fuels, which are a key component for carrying fire. So it's interesting, with Barger's work, they did a nice study looking at an area, and they found they were looking in basically a persistent woodland. It was relatively open. They did see infill occur during this time period, but they found little evidence of fire, and there was no livestock grazing on one of their areas. So their conclusions were livestock really had a minimal impact on this area, but probably fire had not had very long return intervals on that, compared to some of the areas that others have looked at up north, where there was evidence of more fire occurring. So let's talk about the regional role of fire. Well, this paper came out by Little that he mentioned between 1980 and 2000 that the sagebrush semi-desert, kind of that sagebrush steppe that Neil West circles north of what they call the sagebrush shrub, was 4 times more likely to burn than the Colorado Plateau. What's gone on since? Here's a fire map showing what's occurred. These are fires that are from 108 hectares or larger, mapped since the year 2000. And you can see a real regional pattern here. Now, this is mixed, this includes also forested areas. This would be the Middle Fork, the salmon and salmon country, and the Bitterroots and the Church. But here we have the Snake River Plateau down and through here. And this would be much of the sagebrush, what West would have called sagebrush steppe through here. And we can see as soon as we move into the sagebrush scrub, fire drops off. Look at the Colorado Plateau through here. Here we have the Uinta Mountains coming down, and this would be the Mogollon Rim where we can see fire increasing, probably because increase in fuels and ignition rates. The colors show basically going from more of a spring fire regime to midsummer, late summer regime. But you can see that fire is particularly more likely to occur as one moves north. There's also variation just within regions. Stan Kitchen has a great paper that came out in 2012 that compared some fire histories between mountain ranges. Biondi, I believe, did some of the same, showing that one mountain range may have had a very different fire regime than another mountain range. And the likelihood of what's going on there is, one would be the fuel component, because of how broken it up was with the topography, and the other one would be ignition. You may have more or less ignition on one range than the next. So The fuel structure, the way it lays across the landscape with topography and ignition are key components. And then we can even get on a smaller scale. This is in northeastern California here, where we did some intensive fire history work, where we have this micro kind of north slope. It counted was about a 20 to 30 acre. We had several of these scattered across the landscape that historically, these are big old ponderosa pine that died back in the 1920s. It's coming into juniper and mountain mahogany. That this had an 8 to 12 fire year return interval, and it was probably a fescue pine site. We move out to the flat. This is a very productive mountain big sage, fescue blue bunch wheatgrass site that probably had a return interval more like in the neighborhood of 30, 40 years, 20, 30, 40 years. But then we can come over to this site where we get a distinct change in soils, not much change in the macroclimate, where we had a woodland, where we had a stand replacement event occur back in 1717, where you had pockets of old trees left, and then a partial, about a third of that burned in 1855, and those are the only fires. So we see lighting up going on in the foreground every 8 to 12 years, and the one in the background's only burning every 100 to 200 years. So again, there's considerable variability. So it's important to keep the woodland and shrub steppes separated. So the question is, what is it that we're restoring when we start talking about restoration? And I think this is going to apply to much of our conference today. And for me, when I think of restoration, I think of what we as managers try to do is manipulate or change vegetation or maintain vegetation, some composition or structure to provide a particular function or a group of functions. To me, the key function that we should all be looking at are what I call the three ecological processes, and that's the water cycle, the hydrologic cycle, and, the hydrologic cycle, the nutrient cycle, and the energy cycle. Cheatgrass having a very narrow energy cycle, very short window, where if we're more into a native situation, we lengthen that growing season. So we want to capture as much moisture, store as much, safely release it as we can, put in as much organics as we can, and really work towards systems that we feel are resilient, that or have the ability to recover with disturbance, and that they're resistant to invasives. Now, this is an easy job on some sites, to all the way to where it's almost an impossible job with today's technology on some of the very harsh sites. And so, but these to me are kind of things to keep generally in mind. Now, to do that, for me, I need to simplify it and get it down to kind of more of a conceptual model or way of thinking, and thinking, okay, you know, what does resilience and resistance depend on? You know, how, when you go from a low or high resilient site, and to me, these are the main components. The ecological site characteristics, which is topography and soils and climate, which will depend on what kind of potential vegetation you have on that landscape. But what you have on there is based on what the potential is and what the disturbance history is. We do deal some with post-weather fire severity, but those are key components that are going to determine the resilience and resistance of those sites. And along with, of course, the post-grazing management and monitoring are going to have impacts also. So if we take a quick look at the key components for what the potential resilience and resistance on that site is, again, it comes down to climate, topography, soils, which determines the kinds of vegetation that can grow on that site, and what the soil moisture temperature regimes that kind of summarize nicely into pulling a lot of those factors together, saying how much moisture do you have for growth, and what time of the year and kinds of temperatures do you have. And temperature is a key component for resistance to some of our invasive species. And of course, disturbance severity is huge, where you could have a site that has those components, and maybe you had good stuff in the understory, but a high severity fire, particularly when we have a dense juniper woodland, we can get over 90% mortality of our deep-rooted perennial grasses that are really, many of them are fairly resistant to fire mortality under more moderate to low severity situations. Well, one thing that is good and bad about living in the Great Basin is that we deal with a lot of heterogeneity because of the topography. And that makes management more challenging, but at the same time, these changes there's some predictable things that happen. We know when we go up in elevation, it warms and cools, and we also know that temperatures and moistures, we know as we move from one aspect to the next, those are some fairly predictable. And in general, just kind of a simplified, knowing there's a lot of complexity involved, that as we move up in elevation and whether we're on a north or south aspect, our resilient increases up to a point, and then we get up high enough where our cold temperatures shorten down our growing seasons. So resilience tends to increase as we go from those low, dry black sage or Wambig sage sites as we move up into our upper sites. Again, we're going from mesic, aritic, interpreting those in English from soils. That would be going from warm, dry, to cool, moist, to cold, moist, as we go cryic to xeric. And the nice thing with that, it enables us to extrapolate. Here's two sites. Both these were very likely mountain big sagebrush communities. They one though is down in central Nevada, and where we're dealing with pinyon, young pinyon, and Utah juniper. We have western juniper, but we would expect the resilience and resistance of these sites to be the same. One's growing on basalts, the other one parent materials is growing on limestone, but if you pull those ecological characteristics together, their moisture availability and temperatures are about the same. Now, because the latitude difference, the site in Nevada is about 2,000 feet higher in elevation than the one is up in Oregon. Here's a site, Oregon up top and Nevada down at the lower. Response very different after fire. Wildfire down below, it was a prescribed burn up above. Different soils, but they should have had the same potential, and it didn't happen. So why? Well, to me, most likely, two possibilities. One was we know this was a moderate severity fire up on top. Down below, probably a higher severity fire. But the other thing is we may not have had the good vegetation in the understory at the time that burned. And the way to check that out is I'd want to move over to this aspect right here, where we know that's going to be a different site, but still, if this was heavily hit by past livestock grazing, then it's likely we're going to be missing some of the perennial grass component on the other. So it's going to need to do a little detective work. Again, high severity fire, but the one thing that this has against it is that it's on a mesic, it's on a warm, aritic site, probably 10 inches of precip, so resistance is going to be low to invasives. The reason why we don't see much cheatgrass in this slide here is because it was a hot fire. The seed was consumed, but cheatgrass definitely has a strong potential of coming in on this site. This is a more productive, higher elevation site, but extremely dense stand. Not much in the understory except cheatgrass. So if this burns and it's a fast-moving canopy fire, we're going to have a lot of cheatgrass seed, and this is going to come into cheat very quickly. If it's a hot fire, we're going to consume most of that cheatgrass seed, so we'll have a good at least 1 year window to be able to go in there and possibly do some seeding on this site, because it would be a stand replacement event. One more example here. Here's one that's kind of up in that cool mesic aritic, so it's about as good of a mesic site as we can get. We have good stuff in the understory, so we would think we'd have a pretty good response on this site, but the one issue we had is where we had the hot spots around the canopy, where we had those duff layers, we have cheatgrass on this site. And just one more, the easy ones. This is a cool site, 12 to 14 inches of precip. We had good stuff in the understory when this fire went through here. It was low to moderate severity fire, you can see, because we have needles left on the tree. No needles on the tree, black bark means it was going to be more of a high severity event. And this is what that site looked like in second year. So these are the easy ones. These are the ones we wish we all could work on and kind of forget about the lower stuff, which are just darn tough. And then one last thing where I wrap this up is the concern that we know this resilience that the basin had in the past is dramatically changed because some of the new species present on this landscape today. And this is with our annual weeds. And the concern, if we were to map where in the Great Basin do we have the greatest potential for cheatgrass, say removing the fire, and if we were back to say all sagebrush, where would the hot spots be? The hot spots would be the Snake River Plateau, the Columbia Basin, the Humboldt drainage, particularly in the Winnemucca area, and there's several hot spots in Utah. What do they all have in common compared to the areas surrounding them? Mild winters and hot, dry summers. So where we feel, well, we have that all over, but compared to, relatively speaking, within the region of the Great Basin, where we have more mild winters and where we have more hotter kinds of dry summers, is where cheatgrass is the most competitive. So what does that mean in the future? We're warming up. It means we're going to see cheatgrass and these natives moving upslope. We're going to see resistance and resilience of our lower elevation pinyon-juniper sites and mountain shrub communities are going to be decreasing as we move into warmer, drier conditions. A little bit of what I talked about with this resilience and resistance, it just came out in these two publications. And I always tell my students, Sherlock Holmes would have been a great ecologist, because being a good ecologist, being a good land manager means being a good detective, where you pull together your own personal experience and experience of those around you and whatever information that you have in the area to let you know that what kinds of sites do you have, so you can stand on a totally black site. And if somebody asks you, what is this site going to look like in 10, 20 years from now, you should be able to come up with a pretty good estimate, knowing, one, hopefully what was there before, but even if you didn't, you know what elevation, what the soil moisture temperature regimes are, and just pulling whatever information. Do you need to seed or do you need not to seed? And many times, and there's a way of quickly, not putting out transects, but ways of really quickly using that experience and looking at a place and saying, here's what likely is going to happen. And we can do that. The more experience you have, the better, particularly the more experience the people around you have. So, thank you.
We have a couple minutes for questions. Alice?
Yeah, I know you're probably loath to generalize like I'm going to ask you to, but in light of some recent reviews in the literature that have been published, I'm wondering your opinion of what the fire return frequency was pre-human establishment, not in shrublands invaded by PJ, but true persistent woodlands in the Great Basin, and whether those fires seem to be moderate or high severity.
Okay, so let me make sure I cut. So what you're looking at is what I think the fire return intervals were in true pinyon-juniper woodland? Okay, well, the answer is simple, it depends. But I'll clarify that. Definitely in the persistent stand, there were several kinds. One is you have some of these open bare south slopes, poor soils. You've got some really gnarly trees growing up at those sites. And those sites, there's no evidence that those have burned. And you can cross-date old wood on those sites to go back over 1,000 years. You get into sites like, well, Lisa Floyd Hanna Mesa Verde is a good example, or some of these, that one big extensive site that I saw, that true pinyon-juniper woodlands that had very little understory because they were close enough, would have had very long return intervals. But where it depends on is we also had these stands that were more open. And that one last picture I showed, very old stand, didn't burn very often, but the more open, the more surface fuels you have, the more potential that site would have for closing down that return interval. And the important thing to think about with return intervals is the variation. I just think of it in terms of, let's narrow it down a little more, say in a wild big sagebrush site. Let's just say we would know the last 500 years this site had a mean return interval of 80 years. But that could mean that, one century it burned 2 or 3 times, and another century or 150 years it didn't burn at all. So what is it? Gould in The Full House talks about that the mean tends to be a dangerous abstract that we tend to make a reality, but it's actually the variability that is the true reality.